Okay, good morning everyone. My name is Sathish Kumar. My subject is DC machines and transformers. Today my topic is winding terminologies and EMF equation of DC generator. Now, winding terminologies in that main part is conductor. What is meant by conductor? A conductor is a material that allows the electric charge to move through the is an electric current. Or we can call also it is an actual armature conductor which is under the influence of the magnetic field placed in the armature slot. For example, you can see here in this diagram, from this diagram A. So this is the conductor I am saying. This is the conductor is a material. It will allows the electric charge. It will allows the electric charge. Okay. Now, so this is the slot 1. This is the slot 2 I am taking here. So in this slot 1 and slot 2, so how many conductors I am placing here? 2 conductors I have placed here. One is a conductor 1 I am placed in, conductor 2 is placed in the slot 2. I am placed the conductor 1 in slot 1 and placed the conductor 2 in slot 2. Okay. Now, before that, what is meant by turn? The turn is the two conductor. Here, these two conductors are placed in different slots. When these two conductors are connected each other, it will form a one turn. It will form a one turn. That is called as a turn. This is the example for turn. That is the example for turn diagram. Now, what is meant by multi-turn coil? What is meant by multi-turn coil? Okay. So now, well, describing this turn or armature winding, the number of turns may be specified from which the number of conductor can be decided. That is, the number of conductors will be is equal to Z is symbol of for conductor. Z is symbol for conductor. So number of conductors is equal to 2 into number of turns. For example, here from this diagram, Z is equal to 2 into number of turns. How many turns are there here? Only 1 turn, because one conductor is placed in the slot 1, another conductor is placed in the slot 2. So it will form say 1 turn. So this 2 into number of turns is equal to 1, then number of conductors is equal to 2. Number of conductors is equal to 2 according to this formula, according to this definition. So then I am getting the Z is equal to 2 here, according to this example. So now we can decide here multi-turn coil. Multi-turn coil is nothing but here. So again, I am placing the conductor 1 in the slot 1 and conductor 2 in the slot 2. So these turns or these coils, in the more than one coil is connected to the one coil side to the another coil side here. So you can observe here, this is the turn, and this total number of turns is called as a coil. This is called as a multi-turn coil. That is called as a multi-turn coil. So for example, see here, coil. So this is the turn in nothing but as a what? It is form a connection of one conductor to the another conductor for different number of slots. It will form a one path is called as a turn and coil. So now in the turn I am getting the coils is there and as well as the coil sides also is there. So before going to definition of the coil and coil side, you can see the examples also. Now you can examples here. First, coil. So coil is the simplicity of the connections. That is, the turn are group put together to form a one coil. Group put together to form a one coil. Okay. So now, for example, if coil contains only one turn, coil contains only one turn is called as a single turn coil. Is called as a single turn coil. For example, if your coil more than one turn, coil having the more than one turn is called as a multi-turn coil. You can see the diagrams also here, A diagram and B diagram. So this is the single turn coil, this is the multi-turn coil. So single turn coil, in case of the single turn coil, it contains only one turn is called as a, that's why this is called a single turn. You can observe here, only one turn. But in this case, number of turns is more here. Number of turns is more than one turn is there here. So that's why this is called as a multi-turn coil. That is called as a what? Multi-turn coil. Okay. So this is about coil. and coil side. So we having the two coil sides from one coil. Two coil sides from one coil. So this is totally is called as a what? This is the coil. This is the singleton coil. This is the multi-ton coil. So each coil having the two coil sides. Each coil having the two coil sides. That is the coil side 1 and coil side 2 here there. So these two coil sides are placed in different slots having a distance of around 1 pole pitch between them. 1 pole pitch between them. So coil side is placed here, one coil under one slot, another coil side is placed in the under another slot. So the distance between these two coil sides, is called as a pole pitch. Then winding is to be full pitch. Now pole pitch. What is mean by pole pitch? The pole pitch is the angular distance between the central of line of one pole to the central of line of the next pole is called as a pole pitch. For example, you can see this diagram. So I am taking here two conductors or two slots. I am taking these two slots having the each conductor here placed here, and the one coil side here, another coil side here, and this is the singleton coil I am taking. So in this singleton coil, center angular distance between the central line of the one pole, this is the central line of the one pole, to the central line of the next pole, this is the next pole, is called as a pole pitch. Is called as a what here? Pole pitch. This is called as a what? Pole pitch. Okay. Pole pitch is always 180 degrees is there, that is regardless of the number of poles of the machine. So then pole pitch is equal to 180 degrees of full pitch here I am taking. So now this is about pole pitch. Now another definition is, another terminology of the winding is coil span. What is meant by coil span? Coil span. The coil span is the distance between the one conductor of certain phase and the corresponding return of the conductor. So you can observe this diagram here. I am taking here north pole and south pole. So this north pole and south pole having the two coil sides. This is the one coil side. This is the another coil sides. Okay. So then this distance between these two coil sides is called as a coil span. Is called as a coil span. This is the definition of coil span. Next, armature winding. Armature winding, coming to construction of the DC machine, we have two types of the windings are there. That is, the one is the armature winding, another is the field winding. Armature winding is called, there are number of armature conductor which are connected in a specific manner as per our requirements. As per our requirements is called as a armature winding. Is called as a armature winding. This armature winding having two types of the armature windings are there. That is, one is the lap winding, another is the wave winding. Lap winding, another is the wave winding. So now we'll discuss about the two types of the armature windings. That is, first is the lap winding, second is the wave winding. What is mean by lap winding? We'll discuss now. Lap winding. Can observe here. In this case, if connection is started from conductor in slot 1, then connection of overlap each other as a winding proceed. Still the starting point is reached again. Is called as a lap winding. Is called as a lap winding. In this case, if connection is started from one conductor in slot 1, then connections overlap each other, winding will be proceed till starting point is reached again. Is called as a lap winding. Can you observe the diagram? So you can observe here, this is the lap winding I am saying. So this is the First red symbol of the red here, you can north pole, this is the south pole I am taking. So two coils I am taking here for the example of the lap winding. That is a coil 1 and as well as a coil 2. Coil 1 is a red color, coil 2 is the green color. So now these are the conductors and these are also conductor. Now you can observe here, according to the connection of the lap winding, the connection is started from one conductor in slot 1. This is a slot 1, slot 2 and slot 2. 3 slots are there here. So these 3 slots, in that 3 slots, starting from one slot, this is the slot 1 started here. Okay. And overlapping each other as winding will be still proceeds here. As winding will still proceeds here. Till starting point is reached again. Reached again is called here lap winding. So starting point here like this, and another coil side of the second two connected at the slot 2, and again start from second coil is started at slot 2 and ends at the slot 3. Ends at the slot 3. So this slot coil 1 and coil 2 are overlapping each other in slot 2. Okay. Now you can observe here. So this is the starting end of one next coil. This is the finishing end of the another coil. Finishing end of the another coil. So mean these two are overlapping each other and closed at the starting point, again reached again here. Is called as a, this type of connection is called as a lap winding. This type of connection is called as a lap winding. So due to this connection, the total number of conductors get divided into number of poles of parallel paths in case of the lap winding, where P is the number of poles in the machine. So number of parallel paths in the lap winding, that is A is equal to P, where A is the number of parallel paths of the lap winding, where P is the number of poles of the machine. So according to lap winding, here the two conductors are, two coils are overlapping each other. So that's why number of parallel paths will be is equal to number of poles in the machine in case of the lap winding. So in case of the lap winding, large number of parallel paths indicates the high current capacity. But high current capacity of the machine. That's why this lap winding is preferred for high current rating generators. This lap winding connection diagram is used for high current rating generators and low voltage rating generators. So because of number of parallel paths is equal to number of poles, so that's why number of parallel paths indicates here high current capacity of the machine. That's why lap winding is preferred for high current rating of the generators only. This is about lap winding. Now you can go for the another connection of the diagram. Another connection of the winding of armature winding is wave winding. So now we'll discuss about wave winding. This is about wave winding. So in this type of connection, winding always travels ahead, avoiding the overlapping here. In case of the lap winding, we are getting overlapping, but in case of the wave winding, we are not getting the overlapping manner here. It will be avoids the overlapping manner. Means it travels like a progressive wave. Hence, this is called as a wave winding. So because of the traveling like a progressive, that's why we are calling as a wave winding. So in case of the wave winding, both coils starting from slot 1 and slot 2 are progressing in waveforms. Progressing in waveforms. So you can observe the diagram here of the wave winding. So in this case also, this is the coil 1 is connection is connected to the another slot, and again coil 2, end of the coil 1 is connected here, and the another coil 2 is connected here and starting the coil 2 here. So means there is no overlapping manner in this case. That is the progressive manner here. This is the progressive manner. According to this progressive manner, that will be forms a one wave. That's why this is called as a wave winding. So due to of this type of connection, the total number of conductors get divided into two number of parallel paths. You can observe here. So one parallel path, these two parallel, second parallel path. Those, if you can take any number of conductors or any number of coils, that all coils are connected here progressive manner. If you are connecting here progressive manner, this are coil 1 and coil 2 are both are parallel manner here. Two number, you are getting what here? Due to of this type of connection, the total number of conductors get divided into two number of parallel paths always. So irrespective of the number of poles of the machine. But in case of the lap winding, that will be depends on the number of poles. But in case of the wave winding, irrespective of the number of poles of the machine, the number of parallel paths will be there. So that's why number of parallel paths will be is equal to always 2 in case of the wave winding. That is, number of parallel paths is equal to A is equal to 2. In case of the lap winding, what I am getting now? A is equal to P, where A is the number of parallel paths, 2 is the conductors here. And here P is the number of parallel paths. So in case of the lap winding, number of parallel paths will be is equal to number of poles of the machine. But in case of the wave winding, number of parallel paths will be is equal to always 2 because of always this is the progressive in wave fashion. So that's why in case of the lap winding, that will be used for high current machines, but in case of the wave winding, it is preferred for high voltage machines. It is preferred for high voltage machines. So if you are comparing the lap winding and wave winding, in case of the lap winding overlapping each other, the coils are overlapping each other. But in case of the wave winding, it will having the progressive manner. It will having the progressive manner, and the number of parallel paths in case of the lap winding is equal to number of poles in the machine. But in case of the wave winding, number of parallel paths is equal to 2. And in case of the lap winding, that will be preferred for high current machines. In case of the wave winding, it is preferred for high voltage machines. So this is the winding terminologies of the DC machine. So next topic is derivation for induced EMF, one armature conductor. We need to derive here EMF equation of the DC generator. Before deriving the EMF equation of the DC generator, we need to derive for induced EMF of one armature conductor. Now, for example, let I am taking here pi is equal to flux produced by each pole in Weber. That is, the number of flux is equal to pi. Here I am taking the units of the flux is equal to Weber. And next I am taking the P. P is the number of poles in the DC generator. Therefore, total flux produced by all the poles is equal to number of flux into number of poles, that is pi into P. Then, and time taken to complete one revolution, that is 60 by N. For complete one revolution, that's why I am taking here 60 seconds. Okay, where N is the speed of the armature conductor in RPM, where RPM is the revolution per minute. I am taking revolution per minute, that is time taken to complete one revolution is equal to 60 divided by N, where N is the speed of the armature conductor in RPM. Now, according to Faraday's law of electromagnetic induction, What is the Faraday's law of electromagnetic induction? A current carrying conductor is placed in the magnetic field. Then you are getting the induced EMF in the coil. That induced EMF is directly proportional to the rate of change of flux linkages. According to that Faraday's law of electromagnetic induction, the induced EMF of the armature conductor is denoted by E, which is equal to the rate of cutting of the flux. Therefore, E is equal to d pi by dt according to Faraday's law of electromagnetic induction, where d pi is the change in flux over our total flux, where dt is the time taken to one complete revolution or total time also we can call. That is E is equal to d pi by dt. Now, induced EMF in one conductor is equal to total flux here. D pi is the total flux produced by all the poles is equal to what? Pi into P. That is, I am taking here pi into P divided by time taken to complete one revolution is equal to 60 divided by N. But as I am substituting here in this equation, then we are getting E is equal to pi P divided by 60 divided by N. Then I am getting pi P N divided by 60 I am getting. So this is the equation for EMF, induced EMF of one conductor, that is one conductor. Suppose let us, there are Z total number of conductors in the generator if you are taking. This is the equation for what? Only one conductor. Suppose we are taking Z total number of conductors in a generator. Okay, and arranged in such a manner that all parallel paths are always in series here. Okay, now because I am taking here for Z number of conductors, what is the induced EMF? That is the induced EMF equation of the DC generator. Now Z is equal to total number of conductors. Z is equal to what? Total number of conductors, where A is equal to number of parallel paths. Then Z by A, here Z by A is the number of conductors connected in series, because I am taking here all are arranged in such a manner that all parallel paths are always in series. That's why Z by A is equal to number of conductors connected in series. Now we know that induced EMF in each path is same across the line, because the all parallel paths are always connected in series. Therefore, induced EMF of DC generator is equal to EMF of one conductor into number of conductors connected in series. This is the EMF equation of the DC generator. Now, what is the EMF of one conductor here? E is equal to P pi N by 60. Into Z by A, because number of conductors connected in series is equal to Z by A. That is simply, for example, this is the wave type of the DC generator. The number of parallel paths is equal to what? A is equal to 2. That is, therefore, the induced EMF for wave type winding of the DC generator is what I am getting now? Pi into P into N by 60 into Z by P. P is equal to what? Z by A. A is equal to what? 2. That is Z by 2. That is P pi N Z divided by 120. What is the units for induced EMF? Volts. This is for wave winding. Similarly, In case of the lap winding, number of parallel paths is equal to number of conductors in one path. That is, number of parallel paths will be is equal to number of poles of the DC machine here. Therefore, induced EMF for lap wound generator Eg is equal to P by A, where A is equal to what? P. Then I am substituting there. Then induced EMF or generated induced EMF is equal to pi into Z into N divided by 60 into P by P. This will be cancelled. Then I am getting pi Z N divided by 60 I am getting. So this is for what? Lap winding DC generator. So this is about EMF equation of DC generator. Now we will discuss one problem. So what I am saying here, a 4-pole generator having lap wound armature winding has 51 slots. Each slots containing how many conductors here? 20 conductors. What will be the voltage generated in the machine when driven at 1500 RPM? Assuming the flux per pole to be 7 milliweber. Okay. So first, what he was asking, induced EMF. So what is the induced EMF of the DC generator formula? Z into N into pi into P divided by 60 into A. Where he was given pi. What is the pi value? Number of flux is equal to 7 milliweber. That is 7 into 10 to the power of minus 3. And number of conductors he was given? He was given. The number of conductors is equal to what he was given? Having the lap wound armature winding has 51 slots. Each slot containing how many conductors? 20 conductors. That is 51 into 20. 51 into 20. That is 1020 conductors are there. That is, again, this is the which type of winding here? Lap winding or wave winding? It was given in the problem lap winding. The number of parallel paths is equal to what? Number of poles of the machine. The number of poles he was given how much? A 4-pole generator he was given. That is, number of parallel paths is equal to number of poles is equal to number of parallel paths is equal to 4. Now, speed he was given how much? 1500 RPM. Then I am substituting these all values in this equation. Then I am getting the generated induced EMF is equal to 178.5 volts. 178.5 volts. So this is the example problem for EMF equation of the DC generator. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.